Professor Karol Zykowski, Geometry of Quantum States. You probably have seen the book, so here is an overview of that subject. 1 hour, Karol.
Thank you very much. It's a great pleasure to be here and to talk here again, in fact. And I'm a bit ashamed because a similar talk was given here exactly 7 years ago. So look, here at the Instituto de Ciencias Nucleares, I even had a chance to visit Puma. First question is, do you know, is the Puma the symbol of the UNAM alive still? Who knows? Okay, and so, which is good. And now a second, more delicate question. I know that Chris Amalis was here, but who of you attended my talk 7 years ago? Not many. You did, yes? Okay. No, okay, which is good. But on the other hand, I'm very pleased that not all of you attended, because my talk is, as you can guess, the geometry of quantum states has not changed so much for the last 7 years, and therefore the talk will be related. Moreover, in fact, I was asked to deliver a talk, in a sense, at the basic level with introduction, and now I see it's a bit strange that this is the talk at the very end of the conference, so now you see introduction at the very end. Well, look, if you look on this set of quantum states, you could, I'm pleased to mention a quotation we took from Bogdan Mielnik, a Polish physicist, by the way, born in Warsaw in 1936, and he passed away just this year, 2019, in Mexico City. He, maybe you know, he was here for many years, and he, as far as I know, contributed a lot to Mexican physics, and also he left several of his students working usually in similar stuff. So he asked the following question: what picture does one see looking at the physical theory from a distance, so far, far, far away, so that the details disappear? Very nice question. And since quantum mechanics is a statistical theory, the most universal picture which remains after the details are forgotten is that of a convex set. So he emphasizes convexity of the set of mixed quantum states, and this was kind of a motto for our book, which we wrote with Ingemar Bengtsson. So indeed, if you start with a finite dimensional Hilbert space, let's say Hn, n is finite, and we know what is quantum state. It's a vector, normalized. In fact, it's an equivalence class. We don't care about global phase. And indeed, qubit, you know, is a quantum bit. So if n is equal to 2, you can basically treat the word geometry literally, because the set of quantum states is nothing else as a ball. So in fact, a set of pure states at the Bloch sphere, you know that state can be parameterized like this. There are many different parameterizations, but this one is convenient, so I use here theta over 2 to have analogy to the geometric, let's say geographical coordinates, like geographic longitude and latitude. And of course, you know very well that the key issue is quantum superposition. Here you have two classical states, you distinguish one axis. Usually we assume that magnetic field or something which breaks the symmetry is oriented, let's say, from up to down. Here you have polar poles, south, north, and then those states are classical, and those at the equator are quantum. There is quantum superposition like state plus or minus. Well, this set of all pure states forms just complex projective space CP1, which in this case is a sphere. For larger dimension, it's not a sphere. Instead of density matrices, it's just a convex hull of this sphere. In this case, it's just a standard ball. And now look, if you have a unitary evolution in the space of projective states, it's nothing else as rotation. You just rotate the vectors which seem to be innocent. Of course, rotation is isometry. The distance does not change. And the standard distance in the space of pure states, this complex projective space, is called sometimes Fubini study. It is a function of overlap. Distance between two states is some function like arc cos of this overlap between two states. If they are the same, overlap is 1, and arc cosine of 1 is 0, as it should be. And of course, unitary evolution can be determined by some Hamiltonian, so you write e to I h t, and then this distance overlap, of course, does not change with unitary, because here u dagger is unitary, u dagger is 1. So then, with respect to any standard distance, I will mention them right away, like Hilbert-Schmidt, Bures, or trace distance, now distance between mixed states, it is invariant. It does not change under unitary evolution. So again, unitary evolution in space of mixed states is like a rigid rotation of this body. Distances, it's isometry, distances do not change. By the way, for me, my background was study of quantum chaos, so somehow people ask, how come? If there is isometry, you could not have an exponential divergence of trajectories, because in quantum mechanics, everything is rigid rotation. It seems like a, let's say, oxymoron or contradiction, but it's not, because to study quantum chaos, basically, you go to the classical limit, so dimension n goes to infinity, t goes to infinity, and those two limits basically do not commute. Now, I will mention classical distances, okay, standard, no, not classical. Standard distances are those distances which, for pure states, depend on the overlap between states. For mixed states, I will mention there are some functions of density matrices like norm, you can have a different norms, like d of rho sigma is equal to some norm of rho minus sigma. You can have like LP norms, for instance, and so on, and you can have many different definitions, but all of them have this property, they are unitarily invariant. However, if you study this problem of classical limit of quantum dynamics, you can ask a following question. You can take some special states which are distinguished, they are as classical as they can be, like coherent states. And well, there are again many different definitions of coherent states. They can be defined, let's say, on the phase space, which could be a plane or even a sphere. And classical means that we wish to have that distance between two classical, so coherent states, should be equal more or less the distance at the place where they are localized in the phase space. And of course, those standard definitions do not satisfy this property, but there is one option, one choice, which we advocated many years ago with my colleague Wojciech Słomczyński in previous millennium. It's related to famous Monge problem, Monge distance. Now it's often called Monge-Kantorowicz or Wasserschein distance. If you ever heard this name, it's also very much related, almost the same. And the idea is the following. You know, Monge was expert, was a French officer at the time of Napoleon. He was responsible for what? For maybe not digging the soil, but designing the fortifications. Well, so something like this. Also Monge, you have Monge geometry and Monge projections and so on. But the idea is very simple. If I may use this object, look, you have the initial position of soil and you want to make a fortification, you have to do something with it. Not necessarily isometry, you can change the shape. And you want to optimize something. For instance, money. So how you optimize money? You optimize the total work, but not against gravity, but against the friction. So in a sense, you have here initial pile of soil, and this is the fortification, and you want to find such a transformation which moves this soil in such a way that the total, let's say, number of length of wheelbarrow traveled is minimal. And this is the idea of Monge distance between any two probability distributions, and we generalize it for quantum mechanics. We just took any state in so-called Q representation or Husimi distribution. So X are now here coherent states. For instance, we are going to use those SU2 vector coherent states, but you can also use coherent states like Glauber on the plane, and then for any density matrix rho, you write this probability distribution Husimi function, and now the definition is simple. The distance, Monge distance between any two states is just Monge distance between two Husimi distribution. And the advantage of this approach is the following. If you have coherent states, they have the same shape. So it's easy to see that the optimal transport is if you don't need to change the shape, you just take the entire distribution and shift it like this. So then this total work against friction is just equal or proportional to the distance how much you have to shift. So again, using your back, you want to shift, put it from here to there, and then without change of the shape, so then the distance is just the length traveled. And this is one of possible distances in the space of quantum state, which is a bit strange because, in a sense, it is not unitarily invariant, but it has this classical property that distances between classical coherent state is just the distance between the 2 points they are concentrated in the phase space. By the way, if there are any questions, something is not clear, please do not hesitate to ask me right away. So here is again a short recapitulation of, do we define the set of mixed states, a set of operators which map Hilbert space n-dimensional into itself. Those operators are Hermitian, positive, definite, and normalized trace rho is equal to 1, which corresponds to the probability, like sum of the probabilities is equal to 1. And then the promised definition of standard distances, like Hilbert-Schmidt norm, trace distance, like trace norm. For convenience, we put here 1/2 prefactor. Then more interesting, Bures or Bure distance is related to fidelity. So fidelity is such a strange quantity. Look here, rho is positive definite. You can take square root of it, and this is to make it symmetric. You take trace. By the way, a small warning, in literature sometimes we use, there are papers where f is this with square, sometimes without square, but basically all the idea works. So this Bure's distance is a function of fidelity. Fidelity, again, is not distance itself. Fidelity for states which are equal is 1. If they are orthogonal is 0, but you can build many different distances based on fidelity. It is related also, like trace distance is related to measurement, Bures to somehow a priori guess concerning random states. And in short, my main messages, there are many different many different norms, many different distances. And in short, if somebody could ask me which is the best, this answer is very simple, but in a sense trivial. It depends. It depends what is the application. It's not like this as one distance is much better than others. For some applications, some distances are better or maybe better motivated by physical arguments. So here again, a short summary. So the Hilbert-Schmidt distance is Riemannian, but it's not monotone. Monotone means that it always does not increase under completely positive trace-preserving maps. Trace distance is not Riemannian, it's absolute value somehow, it's not Riemannian, but it's monotone. And from this perspective, Bures is somehow better. It has in this table 2 times yes, so Riemannian and monotone. So monotone here is you see the definition. It means that it always decreases or non-increases under action of quantum operation. Quantum operation, maybe you know, or other quantum stochastic map is map which is completely positive and trace preserving. And then there is an important theorem by Morozova and Chentsov that classically there is kind of one distinguished distance related to Fisher, which satisfies those 2 conditions, and then in quantum case, you can generalize it in many different ways. In fact, there's infinitely many monotone Riemannian metrics, which basically shows it's not like this that you have one different distance. Each metric defines a distance, and you can argue which is better. It's good to know that there's many of them. Second thing, it's good to know we are discussing geometry of quantum states. So you could say, for qubit situation is simple. It is a ball like this, so sphere, Bloch sphere, and inside convex hull of a sphere is a ball. And you like the ball very much, we know ball very much, but of course this is under assumption that we use the Hilbert-Schmidt, so Euclidean. Hilbert-Schmidt, once again, is like Euclidean distance, which is true, but of course it depends on the choice. If you take different metric like Bures, situation changes. In the case of Buer's metric, a function of fidelity I mentioned before, there is a strange situation which is not so easy to visualize. Why? Because you need 4 dimensions. I don't have it here in Mexico. I was not allowed to take any 4-dimensional objects with me. So here is a Hilbert-Schmidt ball of states. Now try to imagine you take this disk and you blow it to change disk in such a way that this point in the center goes to the pole and the points at the equator are kept there. What you get a hemisphere. This is simple. And then from the Buer's perspective, the set of mixed states looks like this. We take the ball, and now we have to blow it, but in 4th dimension, which is not allowed here. And strangely enough, now this corresponds to the circle is like a sphere, so S2 CP1, and the center of the ball, so this one, the center inside, is blown exactly here at the pole of this hemisphere S3. So in a sense, from the Buer's perspective, the set of mixed states for dimension 2 looks like a half of the sphere of S3, which lives in 4 dimensions, therefore is not so easy to imagine. And what is the advantage? Very simple. If you have a hemisphere, you can take any 2 points at the sphere, also at the larger sphere, and you can find geodesic path. So it's inside the ball. It's not so. It depends also on the geometry, but sometimes it's not so easy to write down equations of those geodesic paths if you work in non-flat space. Only in Euclidean space it's simple because we know geodesic is a straight line. In other geometries, this is not simple, and for Buer's, again, we have a nice property because we somehow inherited this property of geodesic, which belongs to the sphere S3, and it's easy to write equations. So here I'm joking that this is a standard ball, and this is a hemisphere, but 1 dimension is suppressed. Are you with me? Is it clear enough? So only short messages that there are many different geometries, many different distances, and you can choose your own favorite one, but practically it means it depends on the application. But of course it's good to know that the geometry is not, in a sense, it's not absolute. It depends on the assumptions done, on the metric used. Okay, so here just to make a short remark related to Krakow, Poland, a picture like this. What can you see? What can you see? 2 gentlemen, yes? And they are talking. And now the more difficult question is what they are talking about. You cannot guess. They are talking about mathematics, of course. It's clear that they are talking about mathematics. In fact, this is Otto Nikodym, maybe you know the name, Nikodym derivative, and Stefan Banach, you also might know the name. And the point is they were talking at a bench in Planty Garden in Krakow. But look, in summer 1916, what happened in summer 1916? So I'm not sure what happened in Mexico in this time. But I know what happened in Poland, especially in Krakow. It was the middle of the First World War. Russian army was very close to Krakow. In 16 was already repelled a bit further. But there were very, very bad times in Europe, especially in Poland. So it was amazing that 2 people were talking mathematics. In fact, they were talking, we know now what about Freshe integral, and 3rd person, already then known mathematician Steinhaus was passing by, and he was so much amazed that in such a city in the wartime 2 people were talking mathematics that he could not help overhearing, approach them and start conversation. Then Banach asked what Steinhaus was working on. It was a paper about some Fourier series, Fourier analysis, and then in 3 weeks, arguably, Banach found, as a young student, by the way, in this time, Banach has not finished studies. During the First World War, he had to leave studies, and he was somehow trying to support himself from teaching math younger colleagues. But anyway, then they met each other, and during all his life, Steinhaus supported Banach and always claimed that the largest mathematical discovery was Banach himself, even though he had a lot of other important discoveries. By the way, it is not so well known, but he discussed fractal sets and fractal curves before Mandelbrot, but this was done in the 50s after the Second World War, was published in Polish journal, was not so well known. So I go back to the space of mixed states, density matrices. So you know the definition. For one qubit, it's just the Bloch ball. In general, it is a larger object, but you can say this is a cone of positive matrices, and one is like a cross-section. So you take a cross-section of a cone. In the case of n equal to, with this standard Schmidt geometry, you just take the ball. So this represents a cross-section of a cone and the hyperplane and gives you a ball. In larger dimension, it's a complicated object which has n square minus 1 dimension. Why n square minus 1? We have Hermitian matrices. Hermitian. So you have n square complex numbers. Because of hermiticity, you have n square 3 parameters. But because trace is 1, you have n square minus 1. And look, if n is equal to 2, n square minus 1 is just 3, and indeed Bloch ball is embedded in 3 dimensions. So for dimension 3, what is the size of mixed states of dimension 3? 8. Can you see in 8 dimensions? No, neither can I. This is the point. It's not simple to work in 8 dimensions. And what we are going to do, okay, if we not understand. So I can tell you, after 20 years working on this subject, I can frankly say I do not exactly understand the structure of this set, even for dimension 3. But I will tell you what I do know. So the question, very innocent, how this set of n equal 3 mixed states looks like, it has no simple answer. Of course, we know it's an 8-dimensional convex set. Of course, it's convex, as Bielnik mentioned. Convexity is the key property. But it has only 4-dimensional subset of pure states. This 4-dimensional is just CP2. This you know. And the boundary is, of course, 7-dimensional, because it's inside this 8-dimensional set. But the set of extremal points in mathematical language, or pure states in physics jargon, is only 4-dimensional. So, in short, I'm not able to tell you how this set looks like, even though I would love to do it, but at least I can make use of such apophatic approach. Maybe you know this word. It means I know how it does not look like. Apophatic means I know how the set does not look like. For instance, why this is a good model how the set does not look like? Why? Okay, where's any student? This is a school for students, yes? So why this is a good model? That it does not look like this? Exactly, it's not convex. So everybody see, it's an example, it's not convex. Sorry? Yeah, okay. This one? Because it's a ball, and we know ball is only for dimension 2. For dimension 3, it's not a ball. Okay? Okay, next, who is the next? Okay, just to check where are other students. Okay, so why this is not like a set of mixed states of size 3? This is a polyhedra. Okay, you can buy a T, but it's a polytope. And we know it's not a polytope. Yes, do you agree? It's not a polytope. Now, as it becomes more complicated, this is nice. Look, it's a cylinder, or in Canada it will be a hockey puck. Because it has some flat parts and has some round parts. So it's already more sophisticated question, so I will not ask, but I will look for a volunteer. Who knows, again, why this is a good model to show how our set does not look like? Now look, a hint. I use red color for something. Red color means what? Well, good, but in quantum physics we don't know what is edge, but we know about what? Pure states, extreme states. So what's wrong about this red circle? Again, apophatic approach. This is a model how this set does not look like. So which important property is missing? Okay, so now professors are also allowed to answer. No, close. The set of pure states is simply connected. From one extreme point, you can get to other extreme point in quantum mechanics just by unitary rotation. And this is not the case here, because here, what are extreme points of a cylinder? Very simple. One circle here, one circle there. So they are not simply connected. So this is a feature which should be for our space 8-dimensional object of mixed states, but it's not there. Yes, are you with me? Okay? So now comes a more complicated case. You see, I rotated, I have such an object with me, but it was too heavy to bring it here. But you can imagine. So look, I will go back. This is just a cylinder. What I've done, I cut it, and there is a nail inside, so I can rotate it, and then there's a special property that this width is equal to the diameter. So if I rotate it, I get such a nice object. And look what has changed now. What is the set of extreme points of this set? It is just the strange superposition of this part, this part, this part, and this part, and it is simply connected. So this feature which was missing here is there. But this is again an example, now again more complicated. What feature, important feature, is not here? Now this set of pure states, extremal points, is connected. Look, if I have this object of dimension 3, somehow threefold symmetry is distinguished. Why? For classical states, what are the classical states? They are 3-point probability vectors. So what they form? They form, of course, equilateral triangle. Because if you have 3 axes like P1, P2, and P3, you put one here, and what you get, this is this shape. So this is, from this perspective, equilateral triangle. So this is the set of classical states, or diagonal density matrices. Simply, this set corresponds to the equation P1 plus P2 plus P3 is equal to 1. So this is an equilateral triangle, and this set should have such a cross-section like this, and there is no triangle somehow, such a nice triangle inside. So therefore, we created another object. No, sorry. Okay, I will skip this. So this is a more interesting object. So you have a triangle, and you rotate it in a such strange way, and then this is a convex hull, which already is more sophisticated, because you see, it has some flat parts, some round parts, and triangle is somehow there. So it's a better model, but of course, it's still not good enough, because it's 3-dimensional. It's not 8-dimensional. But this basically shows how interesting and involved this structure might be. So I produced, no, not wrong, not I brought to you pictures produced by my former student Konrad Szymański, but they are in fact not pictures. They are 3D pictures, 3D outprints, so I will pass it through. So in a sense, what you see, it is more or less like 3-dimensional projection of the set of states from R8 to R3. Because what we usually observe, look, what we observe, let's see if I can do it. No, okay, I can. If you have an object, I can put it, let's say here, and look at the shadow of this object at the screen, yes, you see? And shadow depends on the orientation of the screen and of the object. So this you can consider as a shadow, 3-dimensional. You put a dimensional object in 8D, we cannot see it, and we project it into 3. And this is how it looked like, and of course the shapes are very, very specific, and then we try to analyze the collection, properties of all possible shapes, how they may look like. So here is just, yes? Sorry? Okay, we can count how many flat faces there are, or edges or corners. Typical, as you can guess, I will mention this, typical projection will have no flat faces, will be like oval shape. But there are many untypical we can study. So here, just to change the topic, a Vistula River Wawel Castle. So it looks like this. Yes, so some of us visited Krakow, for instance, Gerard, and now we can confirm it looks like this. Unfortunately, this year we don't have so much water. We are in problems, so there's kind of not enough snow, not enough water, but it's not so bad still. And here I discussed apophatic approach to the set of mixed states, but now I just mentioned that there is a chance to do something more constructively. We take this 8-dimensional object and we analyze all 2D or 3D, or cross-section or projections. It's not exactly the same. You see, projection is, it can be orthogonal, it can be projection on the screen, or you can have a cross-section and study how the cross-sections look like. Of course, this is only partial understanding of the set. But of course, even in 3D, if you consider like tomography, many different cross-sections, you can get a good image or good understanding of the set. Of course, to have a full tomography, in principle, you need infinitely many cross-sections. Yes? And then I'm just will mention that those same tools can be also used if you have n not prime, not 3, but for instance 4, where you can define bipartite systems, separable with entangled states, and you can study properties of those. So here's some short mathematical notion, and it's also very well known in some field of algebra. It's called numerical range or field of values. But look, from the classic quantum perspective, I use now quantum notation. It is for any A, it's just set of possible expectation values of an observable A. X is my state, which is normalized. And I ask the following question. What would be the set of all possible expectation values of a given observable A? Now, if A is Hermitian, in mathematics it needs not to be. In physics, observable usually are Hermitian. Of course, if there is Hermitian, the spectrum, if observables of size n, contains n eigenvalues, which we can order. We can find the smallest and the largest one. In the case of n equal 4, we have 4 eigenvalues, and it's very easy to show that those expectation values, they are real numbers from smallest to the largest eigenvalue. Therefore, it is somehow a range. This variable can admit any value at the range from the smallest to the largest eigenvalue, and therefore it's called numerical range of some operator. So in short, for Hermitian operators, it's just range from interval, from the smallest to the largest eigenvalue. But in general, you can also have, in mathematics, non-Hermitian operators, and then there are famous theorems which are also like 100 years old. I think there was a conference in Japan because this Teplitz theorem was, I think, proven in 1921. So I think because of COVID it was shifted a bit, but it was just 100 plus epsilon years. So this is really a classical mathematics. And then Hausdorff and Teplitz showed that this set is convex. By the way, I claim now, so they didn't care about quantum states. But I claim now, we are now 100 years later, we are a bit more, maybe not more educated, but know different fields of science. This is the same convexity as the one of Mielnik. Mielnik told us that the key property of quantum states is convexity, and I claim that there is a relation between this convexity of Hausdorff-Teplitz and this one of Mielnik. So some examples. For a normal matrix, normal is a matrix which commutes with its adjoint. The theorem also of Hausdorff tells that this set is very simple. It's just convex hull of eigenvalues. Here's an example of size 6. You have 1, 2, 4, 6 red dots. They denote complex eigenvalues of a normal operator of size 6. So if it's normal, it's a polygon. It is just a convex hull of finite number of points. And in a generic case of not normal, it contains of all eigenvalues, but it can be larger, and this set is somehow can be oval, can be rounded shape. And of course, this is known in mathematics for 100 years. But what was not known, I think, 50 years ago or 40, it was relation of this simple mathematics to our set of quantum states. But just a few other examples. If I have such a normal matrix of size 2 with spectrum lambda 1, lambda 2, then this theorem tells you it's a convex hull of 2 points, so just interval. If it's of size 3, you have 3 points like here, and there's a convex hull of 3 points. It's just a triangle of any shape. So for n equal 3, it must be for a normal matrix, it must be a triangle. By the way, and this such a triangle, or such a line here, how it is related to our space of states, quantum or classical? Any ideas? Any volunteers? This is a school, yes? So in school you can ask questions, and you can ask students to answer, yes? So I'm allowed to some extent. Okay, so who would like to, look, what is the interval? Well, it's just a set of probability vectors, p1 minus p. In a sense, it's a segment of a line, and you can rotate it. For n equal 3, it is just this triangle. But this triangle is equilateral. If you change the orientation of the triangle, the shadow of this triangle could be such a triangle. So in short, you can realize there's a relation between those numerical ranges of normal operators and projections of the simplex of classical probability distributions onto a plane. And okay, so here is such a question now. If you take not normal operator, so if it's a normal, then for n equal 2, we know it's a closed interval. If it's not normal, it's elliptical disk, a theorem from 1932. So we'll celebrate 100 years soon. Okay, and this explicitly, you have a dagger, you can find eigenvalues, you can write equation for this elliptical disk, you know, minor, larger axis, everything is known. For instance, in the case of Jordan matrix, 0, 1, 0, 0, very famous matrix which you cannot even diagonalize, then you can check that then this ellipse reduces to a disk. Okay, and what is the relation to quantum states? So we know that set of quantum states for n equal 2 is just, from the Hilbert-Schmidt point of view, Euclidean, is just the ball. And now look, what could be the shadow of a ball? Of course, it can be a circle, but if you tilt the screen, it could be ellipse, but not more. Of course, in extremal case, it can reduce to the interval. So now you see, there's a relation, because those ellipses of Moore-Nagam, it is nothing else as projection of the space of mixed states on the plane. Because if you have a Bloch ball, any projection, okay, I can demonstrate it even here, it will be a, It will be here a circle, but if you rotate, I'm not allowed. If you rotate the screen, it could be an ellipse, yes? You can imagine. Well, this is again simple for n equal 2. And for n equal 3, it's more complicated. Okay, so here n equal 2, I will skip this, return to this problem soon, but here is a Wawel Castle in Krakow, again the Vistula River. And now look, sorry? View is different. Yes, the castle, exactly, you are right. It was view from this side, now it's from this side. And now a question, is it possible to formulate a mathematical theorem related to this photograph? You might think it's difficult. This is true, but if you really want, you can. So here is theorem of my friends Danuta and Krzysztof Ciesielscy, which goes as follows. With probability 1 minus epsilon, the bench Banach talked to Nikodym in 1916 was localized in eta neighborhood of this red arrow here. And of course, it's difficult now to find analytical relation between eta and theta. This is not known yet. But in this very place, if you ever have a chance to visit Krakow, if you go there, you will see such a plate. So here is a long story in Polish. This is just plate commemorating this famous discussion between Banach, Nikodym, and later Steinhaus. And in English version is shorter, Otto Nikodym on the left, Stefan Banach, in conversation about mathematics. This bench memorizes their famous meeting with Hugo Steinhaus in the Planty Garden in summer 1916. And here is a booklet about Stefan Banach, remarkable life, brilliant mathematics. In fact, he was born in Krakow, then he moved to Lviv, now in Ukraine, returned to Krakow. He got a position after the First World War at then it was Polish University in Lvov, and spent all his life there. He survived the war, but was so ill he eventually passed away just in 45. He got the position in Krakow, but could not accept it because he didn't manage to survive and to come to Krakow. So we now just mentioned that then if you have objects 3-dimensional or even 5-dimensional, you can look at their shadows. Here is like a shadow of a full tetrahedron, of the hollow sphere, and of the full ball. And from those shadows, somehow, you can get some information about the many-dimensional object. So now comes a concrete statement, a mathematical statement. In short, if you have the set of classical states, it is just a regular simplex, like this triangle, and then the set of orthogonal projections of this triangle or simplex on the screen is equivalent to all possible ranges of normal matrices of order n. And the similar statement holds for quantum states and not normal matrices. In short, all possible numerical ranges correspond to some projections of this set of quantum states on the plane. So studying those objects, we can get some information about structure of the set of quantum states of a given dimension n. And here are some, again, examples for n equal 3. So you can get a triangle like this, a set with 2 lines. This is convex hull of an ellipse and the point here. A set with 1 straight line. And the generic picture is such a oval-like shape without any straight lines. So here green are eigenvalues, and this is like probability distribution, which shows that the probability distribution is more concentrated close to the center. So those results are only 30 years old. There was a paper by Keeler which made this full classification for dimension 3. So in a sense, this object I sent to show to you, where is it? Somewhere. It's okay, so if you make projections of this set on the plane, you will get one of those 4 classes. Okay, and here are just examples I mentioned, discussed in our paper with Konrad and Stefan in 2018, and there are some, we classify here all of them for n equal 3, so this is the main hero, and look how he is doing this object you have seen here. He already got the PhD degree a few years ago, and was a postdoc in Germany, now he is postdoc in Slovakia, and we'll see what will happen. So the main object is a good student and his program here, and the machine to do it. So here are those shapes. We managed to classify all those shapes for n equal 3. There were like 10 classes, as you mentioned, depending on the number of faces and the quality of the faces, so the number of lines in the faces. This was done relatively, rigorously for dimension 3. And then this again the list of examples for n equal 3. And now this year, okay, in fact last year we tried to generalize it for n equal 4. We got some constructive, you see almost the same team results, but this is, as you can guess, much more complicated. And for n equal 5, well, the set is so complicated that it will be pointless or difficult to try to enumerate all possible shapes. But now look. You can ask what happens if n is not 3, 4, 5, but let's say 7, 10, 100, or 200, or goes to infinity. And there is a strange situation. Why? Because you can guess the larger dimension is complicated. On the other hand, there are some other arguments which tell us that the larger dimension, the life becomes somehow ironically easier. Who knows why? What happens in larger dimension? Who of you knows high dimension? How the geometry looks like in 1000 dimension of 1001, for instance? How do you think? Now maybe 500 for you. Have you any imagination? But look, I will tell you something. Some French people are clever, and they have a good imagination. So there is a question: how a cross section of a cube looks like? It's very simple. You have a cube. So what is the cross section of a cube? You will get what? polygon. How many? No. Can you have pentagon? No, yes, you can. You have to have a cube. And you can find such a cross section that is a cube. Can you have a hexagon? Even it can be a regular hexagon. But now look, you have a hexagon. Means 7. No, why not? Because it has only 6 faces. So each side is obtained crossing a face. So if you have 6 faces, you will have not more than hexagon. But if you have 4 cube in 4D, which is difficult to visualize, but you make a cross section, what can you get? Octagon. Because there are 8 faces, yes? But if you have n cube, n is arbitrary, you can get a polygon with how many? 2. A polygon with 2 n sides. Look. And yeah, can you guess? Of course. If you have polygon with 100 sides, you hardly see that it's polygon. If you have 1,000 sides, so any person will say, it must be a circle of an ellipse. So here is a look. The important mathematical statement is by Dworetzky, very innocent title, Some Results of Convex Bodies. But look, there's a strict mathematical good theorem with certain technical assumptions, but the statement is very simple. If you take a generic object, and it's a compact, high-dimensional, convex, then you make a cross-section, what you get? A disk. So almost like elliptical disk. Why? Because in principle it's almost a polygon, but poly is so large you will not see it. We will be very close to the disk, and here you can read it for us in a good French language. Quand le cube est rond, which means that the cubes become round, which is strange. And this is those people I want to advertise very nice web page. And in this web page of Guillaume, you can find nice pictures which basically show that typical cross-section of such a cube in high dimension is almost round. And here is just our remark on random matrices of Genib matrices which are normalized. Genib are basically, it means that there's a Gaussian entries without any symmetry, they are not Hermitian. If they are not Hermitian, they are not normal, then the red is eigenvalues of size 10, 100, 1000, and then you see this numerical range, which practically is just projection is closer and closer to the disk, in this case, a circular disk, and one can show a mathematical statement that with measure 1, with probability 1, for n going to infinity, this object will be very close, so converges in Hausdorff distance to the disk of a certain radius. So this means that typical, so again, for large n, the set is very complicated, but you will not see those complications because typical cross-section or typical projections will be close to a disk. Okay, so this is the statement. By the way, there's another French here person, this team, you know, Benoit Collins? Yeah, who is known for many different results. So this is kind of a relation to the Dworetzky theorem because it means that the set of mixed states is convex, is well behaved, and for large n, it's very complicated, but its projections behave well, are very close to a disk. Okay, so now you can ask, well, where is physics? Okay, I discussed something, geometry of states, some mathematics, but where is physics? Yes? Can you go back to the theory? Sure. Okay, but simplex in German, yes and no, because this is typical. So typical cross-section means Genib matrices are not normal. So basically we study quantum, this shadows projections of the set of quantum states. And if you have norm simplices, it corresponds to the probability. No. So what I'm saying is that you also will get the cross-section of the simplex will also become round, like in this theorem, but the convergence is somehow weaker. So you have to wait longer. You have to go with n higher to see it. Well, the simple argument is, if you have a cube, you have two n faces. If you have simplex, you have like one face. So you see, the polygon will have typically less sides, yes? But for n going to infinity, both are the same. The convergence rate will be different. But thanks for asking. So, look, I was asked somehow to present a very elementary talk to, let's say, to the high school students. So I ask, well, if you kick the ball, what will happen? Every kid know that the ball will stop at some point. And if you buy an ice cream, what will happen? During this temperature, this you know. It will melt. So what about entangled state? I have not defined, but you know what it is. And you do nothing. Create entangled states, you do nothing. You wait a bit. Happened? What will happen? Entangled state lose their properties because of something. Because of interaction with the thermic field, and so is the case with entangled states. So in a sense, well, we can say, they will decohere to a separable state. Maybe the decoherence time is different for ice cream and for more or less similar. For ice cream, fortunately for us, it takes longer. For entangled state, if there is 10 to minus 6, 10 to minus 5, it's extremely long time for them. So, now a short remark about composed system entangled states. To have entanglement, you need two objects, like one object here, one object there. You have composed Hilbert space. You define separable states. Separable means there are states which do not interact. You can do whatever you wish with them separately, locally. But you have all states which are not of this class. Now I mean pure states. And the most famous is, of course, the Bell state, which shows the complete correlations, absolute correlations. If you have two coins, you throw them, they are still in the air, but you know that if one, you observe here, let's say head, and you will observe heads over there, even though they are far away. It's, of course, does not contradict special relativity because you cannot convey information. They are only correlated. And to measure entanglement, you can use this entanglement entropy, which is nothing else. You define partial trace. So you have two objects. You each over one, you state of smaller size. It's called reduced density matrix sigma. And then this entanglement entropy is just von Neumann entropy of the partial trace sigma. The more this state is mixed after partial trace, the more initially it was entangled. And then this Bell state can be called maximally entangled because its entropy is maximal. In this case, it's just log of 2. And this picture is just, you take the four states like 0, 0, 1, 1, 1, 0, 0, 1, and you plot at the different colors entanglement. So some sites are separable. Why? Because here you can see 0 is the same. So this site is separable. Let's say at this side you have 1 at the front is also does not change. You have separable site. But let's say here you have 0, 1, and 1, 0. Inside you have entanglement, and in the very center you have just psi plus here, phi plus, so different two superpositions. So this is like tetrahedron. Again, the set is multidimensional. This is a cross section, and I'm proud of it because it became the cover story of our book. And then some people were claiming, but this is not perfect. Let's go back. You see here, this, I was gluing it here, and here some was not glued perfectly, but then I can confirm and claim I did it myself. It was a long time before the artificial intelligence could produce such nice pictures. It was really, I produced the blueprint and glued it together and took a photo of it. So here is kind of, here is just a mistake. It's not so precisely glued together. So this was the first copy of the book with Ingemar Bengtsson. This is the first and key author. And the second one already contains some parts about multipartite entanglement. For instance, this is the visualization of GHZ states in the following sense. Those famous Borromean rings have the property, if you cut one ring, two others go apart. And the analogy is the following. You have GHZ state, and remove one. So make partial trace over any of those three. Those two which remained are separable. So this is a very nice visualization. And then, well, you can also define it for mixed states. It's a bit more complicated. Separable mixed states is just a convex combination of product states. Entangled are those which are not of this form. And perhaps you know that it's not so easy to find the answer. If a given density matrix can be written in such a form, this separability problem is solved for 2 times 2 and 2 times 3 problem sizes. There's a famous theorem of Perez and Horodezzi, and then you can compute explicitly entanglement by the formula of Wouters, and this is so-called PPT criterion of Perez-Horodezki, which means if you perform partial transposition on rho, and this is positive, then if and only if rho is separable for small system, 2-qubit systems. So in a sense, if this is the set of mixed state, this set of mixed state, this will be partial transpose. It will be like reflection of it. The set of separable is just intersection of those two sets. So those are PPT, are separable, those are entangled, and then in the center, this state is maximally entangled, and then there is a ball around this center of the body of mixed states, and with Marek, we had a paper about it written some 25 years ago. We can celebrate a silver anniversary of this paper, yes. And we are still alive, as you see. So there was another paper. So if you go to Oaxaca, you are invited to, you will meet Anna Sampera. She co-authored the paper with Paweł Horodecki, Maciej Lewenstein, where basically it is the same statement. If you take eigenvalues of 2-qubit states, then in this space classical, by the way, this is a classical set of eigenvalues, so probability simplex. If you have a set which is mixed enough, is close enough to the maximal, to the center of the simplex, then all those states are separable, and then there is again the issue of absolutely separable states, which are separable for any global rotation, also introduced in the paper with Marek. Okay, so I think I have to, I only mentioned this picture from the paper of 2001 with Marek, and then just to, I slowly, I see my time is almost over, so I will show you first Stefan Banach sitting at this bench close to Wawel Castle. I already advertised. And then this bench was opened exactly 100 years after this famous discussion. There is something about quantum maps, environmental form, Krauss form, but I have no time to go into details. I will only mention that you can choose some arbitrary exemplary dynamics, even working in the case 2 times 2. So you took it's called 1-qubit Pauli channel, and you act on 1 qubit, you do not touch other. It's relatively simple, or amplitude damping channel. What for? To show such a model, which is non-unitary dynamics. You see, it's non-unitary, it's Krauss form, it's CPTP quantum operation, to analyze how the entanglement evolves in time. And here it is. So here is, we start with some maximally entangled state. Maximally because we rescale this unit, so maximally means this entanglement is 1. And here, for this is some 2-qubit model, we look after discrete number of iterations, how the entanglement changes. Sometimes it goes down and eventually decays. Sometimes they were a different scenario. At the beginning, we had no understanding why it is so, what those revivals of entanglement mean. There was another strange situation. Entanglement goes down, stays 0, and then it can revive or not. This was called sudden death of entanglement by late Eberle, 2003, but we had a paper with Paweł, Michał, and Ryszard Horodecki in 2001 about it. Look, it looks like this if you have a nice curve and you cut it here, because this function, like entanglement or concurrence, is maximum of 2 values. So we had the following picture. This is a set of separable states, and here is the trajectory. Unitarily, you will have an oscillation. If it decays, you have decaying oscillations. But if you have a trajectory which goes fast to the center, you will have entanglement sudden death because it dies there and stays there for forever. And look, this was our, let's say, picture. I can call it like artist-like vision. But you see, it's a 15-dimensional object. So it's difficult to imagine how it is. And 10 years later, maybe 15 years later, we produce such a picture, which then here is exactly this numerical range. Here is a range among entangled separable states. So here are entangled states, here separable, and this is a trajectory. So you see, this confirms somehow the intuition we had many years earlier, which explaining somehow, maybe not exactly, but with hand-waving arguments, the possible scenario of dependence of entanglement in time under non-unitary dynamics. So unitary would be only rotation, non-unitary is like rotation and convergence somewhere, for instance, to the center. So I think I'm almost about to, but I will also mention some nice pictures by Gil Kala, well-known, such a nice analogy concerning quantum, a lot about quantum computing. With noise, there are two alternatives, or optimistic one. Real of noise quantum systems, and you can have a nicer possibilities of. There is another pessimistic vision, then low degree polarity, basically that the issues will of quantum, and then the quantum computing could be a fantasy and illusion which will never, like Fata Morgana, a word which will never be achieved. This was written in 2016, so 10 years ago, and to tell, we still don't know which picture is stick. Let's say. So I want to show you that use some simple geometric tools get better understanding of the set of complicated for n equal 3 and more complicated for 5, 6, 7, and then somehow ironically and going to infinity in a sense that it's so complicated that it becomes simple. Again, properties are to describe, and then we can learn something studying those shadows or numerical ranges about structure and geometry of the scene. So the set of quantum states is in the scene where all algorithms of quantum information processing are, they are written for such to be executed. And then this geometric approach is useful, for instance, to study quantum entanglement. It can allow us to explain the effects of entanglement revivals and entanglement sudden death. But of course, it's more work still to understand consequences of noise and decoherence for all the schemes of quantum computation. And here this is just the final picture of bench. And you see here are some equations. Here, Godin and Stefan Banach talking about mathematics in summer 1916, and then this bench was opened in Planty-Garden in Krakow already 10 years ago. And if you ever come to Krakow, please go to Wawelkasse and you can find this bench. Thank you very much. This is all. And sorry for speaking too long, but only 3 minutes.
Any questions?
Please. Some questions.
Thanks for your talk. I don't understand why the separativity criterion works only for spaces of 2 and 3 dimensions and 2 and 2 dimensions.
Okay. The question was concerning PPT, positive partial transpose criterion, yes? Okay. So here again is a strange miracle that it is related to some mathematical statements which are related to 2 names. One is Polish. So there is a theorem by Sturmer plus, okay, and Voronowicz. Voronowicz is a Polish mathematician, he's still alive, and in short, this theorem says that if you have any map of size n, which maps the set Mn into Mn, for n equal to, all maps are decomposable, which means that any map can be written like phi, which is, sorry, any positive maps, all positive maps, Pp, can be written as phi completely positive plus, let's say, alpha t times phi Cp, where phi is transposition. And then using this fact, you can see that there are no other options than partial transpose, which is exactly means that you perform transpose at one subsystem, will give you criterion which goes in two directions. However, for n larger or equal 3, this theorem says that there exist non-decomposable maps, positive maps, such that such a decomposition does not exist, and those non-decomposable maps are responsible for the fact that partial transposition criterion does not work in two directions. So this is related with such another theorem by Horodecki family, that a state is separable if it is, you take any positive map extended by one, act on rho. If this is positive for any phi p, then this rho is separable. You understand? So if it would be completely positive, then of course this is true. But if it's positive, then this one has to prove it. And using this fact of decomposability, this implies the theorem about PPT, which works in positive partial transpose, which works in dimension 2. For dimension 3, there exist non-decomposable maps. By the way, first example, very well known, is called Choi map, by this guy Choi, which was related to this Choi theorem, a different one. And then it means that there exist states which are PPT but entangled.
One more question.
Maybe two more.
Yes, so you were talking about the sudden death and revivals on the
Yes.
entanglement. So can you elaborate further? Because you had there also a graph on this relation that the maximable separable states had anything to do with that. So for me, it's not entirely clear. I mean, if you can just elaborate further.
Sure. So, okay, I will try to. So maybe you could now rephrase your question again.
Yeah, so for example, in that graph, 0 and 20, there is only at 0 on the entanglement.
So here are two different realizations.
Yes.
One is, let's say, with one curve, second is another curve. So again, as we could have no understanding at the beginning what it means. But now, look at geometry. One is, sudden death is like this, crosses, this is a set of separable states. So it crosses set of the border and sticks there and goes there forever, sudden death. Okay. However, another scenario is this green line. But you can imagine such a line that it goes again, and be this case. Goes to 0, then revives, and it may revive again. It depends what is the ratio between unitary dynamics, which turns the state around, and this decoherent part, which brings it to the center. Okay?
Any more questions? Last one. That's the last one.
Behavior, I think that the measure of entanglement that you're using, I guess that...
Yes, yeah. Of course, the actual value will depend. But goes to 0 and stays there or revives again, usually does not depend on the quantity. exciting, amazing, and not understandable was different scenarios that, or you can have such a, let's say, damped oscillation, or such a strange oscillation that he could have exactly the sudden death. It was first understood, and my claim is that with geometric sight you have a better understanding of it.
So let's thank our speaker again.
Thank you very much. Thank you for listening.
And thank you all for having the tenacity to stay here all the way. And I hope it was useful to you, entertaining. And I thank all the speakers of the course. And some of us will continue on to Oaxaca and have more discussions there. Thank you.